So yeah, here we are again with this current problem that is the n queens problem. It is a very good problem for understanding the backtracking. So for this current problem, what the actual statement is that in for an n cross n chessboard, it's a blank chessboard initially. So what you need to do is to place n queens, n numbers of queens. Remember that this is an n cross n chessboard, and you need to place n number of queens in such a way that no two queens should have a common column, should have a common row, and should have a common diagonal. So these are the three conditions which you need to follow for this current problem and for finding the solution. So generally, these problems are understood by the use of backtracking in recursion. So a general approach of backtracking is that for a given solution, while you are on a certain step, you find that after proceeding the solution further, you won't be able to find a correct answer to this. So you just backtrack to the previous position where you've actually made this decision to come here, and you choose a different route for finding the solution. And you use this thing, you use this backtracking phenomena for multiple numbers of times till you get the position or till you get your solution correctly. So this is actually an optimal approach to solve these kinds of problems, since for each number of queens you need to check whether this is following the three criteria which have been mentioned above. So you need to check all the possibilities. So in case where we are actually checking all the possibilities, so then the backtracking actually works well, especially for this problem. So just as you can understand from this diagram, initially the board was empty, the chessboard was empty, and you filled it here. This is the correct position for a single queen. Now, after filling this here, you just find out these two queens share a common row. So this is not a correct position. This is not a valid position to place a queen. Now, even for this one, they share a common diagonal. For this one, it's a correct position. So you now recursively get inside of these scenarios. Now, for the third column, this is not a correct position, especially this. Now, as you can see, for this column number one, we are going for zero index. So this is column number one. So for this column number one, if you are placing this queen here, then there is no place for the column number two where we can place a queen. So this is not a correct choice to place a queen. Even this is a correct configuration for two queens, but since we find that further we could not find any particular solution which is valid one, so we just backtracks from this. So we are just backtracking from this to this, and after this we find out these are not correct. So we are again backtracking, and after backtracking we are choosing a different route. That is this one. And a similar way, after going through all this, we just find out that okay, after backtracking from here to here, then to here, then to here, then to here, and just choosing a different route. And then we find that okay, this one is the correct solution for the given problem. So see, as you can see, for finding a single solution, how many multiple numbers of cases we have covered. So this is genuinely an expensive uh, computation, since we have to check multiple numbers of cases and we cannot miss a single case. We need to check every case till we find the solution. The point where you find the solution, okay, when things work out, we are going back. We are just returning the solution. But until you find the solution, you need to check every possible scenario, which is really hectic for this particular type of questions. So now for these things, you have two different ways to follow this approach, follow this question. That is whether first you go by columns or you go by the rows. By going by column, I mean you fill the queen for a particular column and you go to the next column and fill a queen there and go to the next column and covering all the n numbers of column. Or you can go by the rows. Filling a row, go to the next row, then filling in this row, go to the next row, and similarly filling all of the n rows. So these are the two approach here. We will look for the column one because the row one is similar. Just changing the variables will do the math. So yeah, after doing this thing, we are actually getting to the main function, that is the code one. We are referring here C++ code. So here this solve enq function has been created. which is actually return a Boolean value. So that if this returns a Boolean value, then we find the solution. So what is the initial thing which you have taken into consideration? It is that you need to have a chessboard to figure things out. And we are making the chessboard with the use of vectors. As you can see, if you just imagine, take n numbers of rows as single entity in a vector, and then take n numbers of column as the particular entity. So we are making a vector inside of a vector. The name of the vector is board, and we are taking n numbers of rows. Each number of rows has n numbers of columns which are filled with zeros. So this is just how is the syntax for making this thing. Initially, the position 0 actually represent that no queen is placed here. If the position would be represented by 1, it means that a queen is placed here. So in this way, what after creating a vector, we are calling this particular function inside of an if statement that if this particular function returns a value that is true, or it could return a value false, because this particular function is actually a Boolean one. As you can see here, it is a bool function, which means it's returning a Boolean value. So what we are seeing here is if this particular function is actually returning a false, it means that this if statement would be resulting into true, and you won't find a solution. Since this is the condition which we have written here, that if this particular statement is true, it means that solution does not exist, and you just returning false would make you out of the whole code. It means that you don't find solution. But if this particular condition is true, that means that if this is true, then false is not equals to true. It's quite true. So this if statement won't work. We won't go inside the if statement. And then we would actually print the solution and we will return true. This particular solve enqueue until will result true when there exists a solution. Okay, so now going inside of this solution, we figured out that since we are filling the row, we are filling the queens in a manner of column wise. So we're actually giving arguments here such as boards, which is the vector we have created, and the column. So the column here actually representing the number of queens which we have filled till now. And since we are going column wise, it means that the column here represents the column which we are currently. Since it is quite clear that the previous column which we have visited, we have filled the queen there. So this column here represents the numbers of queens which we have filled. So since we have to fill n numbers of queens, so if the value of column reaches n, means that all the queens are being filled, and that too would be in current man that too would be in a correct manner since we are writing a code in such a way. So if n numbers of queens has been reached, it means the value of column has been reached to n, it means that the chessboard has been filled with n queens and you return true. So here this for loop, now here comes the main part. This for loop is actually representing the numbers of rows. It means the iteration here representing the numbers of rows. So what we are currently doing is for a particular column, we're actually checking each possibilities. For a particular column, how many possibilities could be there? There could be 8 possibilities. There could be n number of possibilities. Uh, n rows are present. So for this particular column, we are checking n numbers of rows that for which particular space would filling a queen would result into a valid answer. So there, this iterator is actually representing the column. Sorry, it's actually representing the rows, and this call is actually representing the particular column which we are in currently now. So for this particular iteration, we are actually checking each row in that particular column that whether is it safe or not. If it is not safe, then we are returning false. It is very clear. But if it is safe, since it is safe, so we can fill a queen there. By filling a queen I mean that you place this queen in the board this and replace that 0 by 1. So we are filling the particular place by 1 and you recursively go inside the next column. Okay, we are recursively calling this function and going inside the next column by doing column plus 1. We have filled a particular column. Since no two queen can share a common column, it means that we need to go to the next column here since we are filling the board column wise. So after filling a particular column, we are going to the next column. So in this way, we are recursively going to the next column by doing column plus 1. And eventually we will find that for a given column, for a given place, after further going, we could not find any valid solution, even if we check all numbers of possibility further. So it means that the current position which you are in now is just not a correct one. So what you do is you backtracks. Since you find that there is no possibility further for a valid answer, you just backtracks to your previous position. So for this position, you actually finds that okay, if this won't result into a proper solution, a valid answer, you will just backtracks. And by backtracks, I mean that you will get back to a previous state, and your previous state before 1 was 0. So now you are actually replacing the 1 by 0 for that particular column. Means that you are just marking it as you haven't visited that column. Okay, you haven't placed the queen there. So this is just the phenomenon of backtracks. Like if you're placing a queen in board which doesn't lead to a solution, then remove the queen from the board. This is the basic phenomenon of backtrack for this particular n queens problem. Okay, so after all these checks, you would result into, at last you will result into this state, and this state would be resulting into true, and after this you would get the answer. If an answer exists, you would be getting an answer. But as you can see, the three conditions which we have initially covered about checking the row, column, and diagonal, we haven't figured it out how to solve this. So this thing actually is solved by this is safe functions, which we have discussed here. This particular function is be checking whether the particular position is correct or not. Since, see, as we've created a function here, it is a very good practice for an object-oriented programming to just summarize the whole code into multiple numbers of functions, which is a good example for a module programming because it enhances the readability. As you can see, it is very clear that this function by its function name that it is checking whether the particular block inside of the chessboard is safe or not. So this is a very good aspect of using modules that are functions for a good modular programming. So after this is a function, what you are particularly doing is you're checking that whether you're in the not in the same row, not in the same column, not in the same diagonal. So as you can see that we are filling the column first. So for an just take an example, we are on a particular column fifth. Since we are filling the column from left to right, so it is very clear that filling the column fifth, after filling the column fifth, it is very clear that the right side of fifth column won't have any queens since we haven't visited there. So how would there be a queen present? And the left side of the column would be having the queens. So we have actually confined our search space by deleting the possibility that there would be a queen present on right side of the road. Since we haven't visited the right side columns, so there would be no queen present there. So we are actually only checking on the left side of the particular column. And also what we are doing is we are actually we are actually distributing the left side in three different ways. That is for the left column, the left upper part, and the left lower part. This is the left row, the left upper part, and the left lower part. It just makes things very clear to understand this. So for the left row, So for that common row, does each column have a queen? Because for that common row, if each column having queen, that means that these queens share a common row, which is just not true, which is just not a valid position. So this would result into false. In the similar way, while checking the upper diagonal, what we are doing is we are decrementing the while going, since just take an example, if you are at origin, you need to visit the upper part of this. Since you need to visit the left upper part, so what you do is to go left and go upper. By going left, I mean that you need to decrement your columns. So here you are actually decrementing column in this way. And by going upper, I means you are decrementing your rows. So here you are decrementing your rows in this way. And you are checking the condition whether this is 1. If this is resulting into 1, it means that there exists a queen, which would be resulting into false. So in the similar way for the lower diagonal, what you are doing is to going left and lower. By going left, I mean you are decreasing the column, and by going lower, I mean you are increasing the rows. And checking if all these three checks are being validified, that means that you are good to go for the particular position, and that would result into true. And in this way, you can find for a particular position whether that queen is placed in a valid way or not. In a similar way, you're checking each number of columns, placing each queen in that particular column, and going to the next one till you reaches n numbers of columns and returning true, and then printing the solution and returning true. So this is all the aspects or that backtracking for this particular n queens problem. It is a very good problem to understand backtracking. Generally, in backtracking, you covers all the case till you find the solution and just go out of the loop. If you don't find the solution, then it means that you are covering each number of cases. So this is a good example to understand backtracking. The time complexity here is definitely n factorial. As you can see, for the particular test case, you're checking n number of cases. And if you reduce some test case, you would be checking n minus 2, n minus 3 number of cases. In the similar way, for each column, you would be checking some numbers of cases. And since all these cases are in recursive form, so what you need to do is to multiply all these with each other. You multiply the time complexity of all these with each other. Since multiplication of it would result into n factorial one. So the time complexity of this is n factorial. N factorial could also be said to be of n square, but since n factorial would be an more accurate way to represent this. So this is an actually all about backtracking. Okay, this is actually a good problem to understand backtracking in its cases and how it's actually works. This particular step is very necessary to follow. That is, while moving back, you just changing it to your previous state. Okay, so this is a common aspect of backtracking, and we are good to go for the next problem. So see you again in another day. Bye bye.